Hello everyone, welcome to our classroom. In today's lesson, we're going to be talking about a very exciting and very important part of our CSEC syllabus, linear programming. In this lesson, we're going to give a basic introduction as to what linear programming is and follow up in a different lesson by doing some CXC questions to give you more practice and a better idea of how to go about dealing with these kind of questions. For our objectives, we will discuss what linear programming is. We will identify and write constraints, discuss the feasible region, and optimize using the objective function. All of these are very, very important ideas that come up in this topic of linear programming. So, what exactly is linear programming? Linear programming is a method of optimizing operations. Let me give you a scenario. A company runs a big business where they do logistics. They ship, they import, they have to manage warehouse space, for example. They have employees to pay, they have overheads such as light and water and other things to pay. And they have a profit to make. They have to answer to their shareholders. Now, how do they manage all of this? How do they make sure that they have the best system for optimizing the space, for making sure that they're making the best profit, and to make sure that their workers are happy and things like those? Linear program is that area of mathematics that gives answers to these kind of questions. And so linear programming is a method of optimizing operations with some constraints. In CXC, they're kept simple, but they will give you a general idea as to how it works in the wider world. The main objective of linear programming is to maximize or minimize, to maximize profits, to maximize earnings, to minimize cost, or to minimize resource usage. Constraints are limits that we have to work with, and these are written in terms of inequalities. And so this lesson is directly tied to inequalities and to drawing linear graphs. Linear programming is considered an important technique which is used to find optimum resource utilization. And so we'll be talking a little bit more about constraints and how to write those constraints. The process provides a clear solution when we are dealing with large data sets, such as the one that I mentioned earlier. The majority of examples in day-to-day applications in business and industry use computers running matrix software to determine solutions. So because there's so many variables in the real world, nobody works them out by drawing graphs in this kind of setting that we do. They use matrix software to solve those kind of questions. But in this section, like I said, CXC keeps it simple. We can find our solutions on graphs, and so we'll be concentrating on those. And so now let's talk about what constraints are. Before I go any further, I want to recommend that if you can find and read chapter 10 of this book by P. Hill, Living Mathematics for the Caribbean, book 4. It's a very, very good book at deciphering and explaining in a detailed and step-by-step way how linear programming is done. And I highly recommend it if you can find that book to read chapter 10 of it. Let's take a look at this example and see how we could probably write down some constraints from this one and to identify what they are. Well, let's look at the problem. A man decides that in order to pay off his debts, he must do some extra work, which is reasonable. Unfortunately, he cannot fit in more than 10 hours of work. If he does extra work during the week, he's paid $4 per hour. He's paid $5 per hour for extra work on the weekend. His wife does not want him to work for more than 4 hours on the weekend. And he doesn't want to work for more than 7 hours during the week, extra hours. So how many hours extra work should he be done during the week and in the weekend to get the maximum wage? And this is our typical question. When CXC gives you those questions, they tend to break it up into pieces, but this is a typical question. Sometimes they are long, it's a lot of reading, but once you get used to them, you realize that they are very, very practical and very, very applicable. Now, in order to write down our constraints, we need to decide on what we're going to use to represent the troubles that he has here. He needs to pay back his debt, and so he needs to work extra hours both on the weekend and extra hours in the week. So let us say, for example, X would represent extra hours in the week. Let's write that down. extra hours in the week, and let Y represent extra hours on weekends. All right, so we're going to right now fix some inequalities in this to describe the constraints that he has, the limitations that he has. So one, for sure, he cannot fit in more than 10 extra hours of extra work. So his extra hours of extra work cannot pass 10 hours, which means that when we add the X hours for extra work in the week and add the Y hours to that extra work on the weekend, that number cannot pass 10. And this is one of our constraints that he has to work with. Second, he has to do some extra work on the week or in the week so that X has to be greater than or equal to 0. Next, he has to do some extra work on the weekend, which means the Y has to be greater than or equal to 0 as well. But there are some more conditions. Here it says, um, okay, let me find it. His wife does not want him to work for more than 4 hours during the weekend. So here we can have that Y is less than or equal to 4 because his wife doesn't want him working beyond 4 hours. But he also doesn't want to work for more than 7 extra hours during the week. So the X here is less than or equal to 7. And so this situation here describes all of these together. X plus Y is less than or equal to 10, X is greater than or equal to 0, Y is greater than or equal to 0, and these two. These describe the constraints. These are the constraints that he has. Constraints. Let me write that better. Constraints. STRAINTS. These are the constraints that he has to deal with. And there's something else in the question that we call an objective function. Might as well mention it here. We're going to do some more work on it later on. The objective function is that thing that we're going to use to maximize, to help him decide what combination of hours he must use to get the most money. So here it says if he does extra work in the week, he's paid $4 per hour, and if he does extra work on the weekend, he's paid $5 per hour. So we can have an objective function here. That will simply say 4x plus 5y, and this will be equal to his wage or his salary. So when we come to the point of finding a solution for him, which we will not do here, this is what we would use to decide what combination of hours would be best for him to use during the week and at the weekend to get the highest amount of money so that he would be happy and his wife would be happy and he can pay off his debts. Let's look at another example. Here, a group of people decide to set up an electronics business making television sets and radios. They realize that with limited working space, they cannot make more than 26 television sets per week and no more than 60 radios. A television set takes 3 hours to make and a radio takes 1 hour to make. In order to be competitive, they plan on making only a $5 profit on each television set and $2 profit on each radio, but they must make a total profit of at least $150 per week. Calculate the number of television sets and radios which can be made in the least possible time to satisfy the given constraints. So one, we need to talk about the letters that we're going to use. So we can say, all right, let X represent the radios to be made, and let Y represent the TVs to be made. Because they have to make radios and they have to make TVs. Once we have decided that, then we can look at the information. They have to make some TVs. So we can say X has to be, radios first. X has to be greater than or equal to 0. All right? Same thing for the TVs. Has to be greater than or equal to 0. And in terms of the number of TVs that should be made, we can see that the number of TVs to be made would be here 26 television sets per week. So they cannot make more than 26 television sets. So we can have y is less than or equal to 26, and for the radios we can have x is less than or equal to 60. That's information that is given here. And so we hello everyone, welcome to class. Today, we're going to be talking about a very, very important part of our syllabus, and that is linear programming. Linear programming is a very exciting part of mathematics. It's a very exciting field in the real world. And CXC gives here a very useful introduction to it. And so we're going to go through what is an introduction to linear programming in this video. In a subsequent video, we're going to talk about some CXC questions on how to go through them. So look out for that video. But our objectives are for today: one, to discuss what linear programming is, to identify and write constraints, to discuss the feasible region, and to optimize using the objective function. All nice and strange terms that we're going to talk about exactly what they mean. And so let's open up by discussing what exactly is linear programming. Now, before I go into this reading, let me talk a little bit about, give you a scenario. Let's say, for example, there is a company. So, for example, a logistics company that does import export. They perhaps the terminal, and they store containers. They ship. They have machinery that are constantly working. They have workers. They have to pay bills. They have to, for example, light and water. They have to pay employees at different levels, from management down to environmental services. And there are all of those things that they have to take into consideration: how to manage their container space, how to make the most of it, and those kind of issues. And of course, they have to contend with how to grow their business, how to make a profit. There's a lot of information that is packed into those kind of businesses that they have to deal with on a day-to-day basis. Now, how do they manage all of those things and make the best decisions to come up with all of those things, to come up with the best solutions for them? Linear programming is one of those aspects that they use in these kinds of businesses and in most businesses. Linear programming is a part of a bigger topic called optimization theory, in which those kind of answers are sought using computer software and persons with those kind of minds to look at those kind of big problems and come up with solutions for them. Of course, at the base of it is mathematics. So what is linear programming? Linear programming itself is a method of optimizing operations with constraints. The main objective of linear programming is to maximize or minimize. So we want to maximize profit, we want to minimize cost, etc. Constraints are those limits that we have to work with. In every situation, there are going to be limits. For example, the container port doesn't have infinite space, and so you have to make sure that containers are moved in and out efficiently so that you don't run out of space. And for example, salary money is not infinite, so budgets have to be made. There are always constraints. Constraints are limits that we have to work with, and these are written in terms of inequalities. And here we have the inequalities coming out to tell you that this topic is directly related to inequalities. It's also directly related to drawing linear graphs, and so those things should be important for you if before you get into this topic. Linear programming is considered an important technique, and it is used to find the optimum resource utilization. The process provides a clear solution when we're dealing with large data sets. The majority of examples in day-to-day applications, of course, they will not be using graphs as we will be using graphs, or you will be using graphs in CXC. Rather, they use computers running matrix software to determine the solutions. And so it's a very, very interesting topic, very, very interesting thing, optimization theory that is used on a day-to-day in large businesses. First, let us talk a little bit about these things called constraints. Before we do that, we do that, if you can find this book, Living Mathematics for the Caribbean, Book 4 by P. Hill, it's an old book, but if you can find it, if you can look in your school's library or somewhere there, you might be able to find a copy. Not sure how it would work in this time, but if you could find a copy, it's a very good read, especially chapter 10 of that book. So I'm recommending it here, highly recommended. Now let's look at a typical question that comes up in linear programming. Yes, they do contain a lot of reading, but they are fun to deal with. And as soon as you start reading it, you realize that it starts making sense and you can relate to it on a day-to-day. So a man decides that in order to pay off his debts, he must do some extra work. Unfortunately, he cannot fit in more than 10 hours of extra work. If he does extra work during the week, he's paid $4 per hour. If he's paid $5 per hour for extra work on the weekend. His wife doesn't want him to work more than 4 hours at the weekend, and he doesn't want to work more than 7 hours extra during the week. So here's the problem. How many extra hours work should he be doing during the week and at the weekend in order to earn the maximum wage? And so before we start scratching our heads and wondering what to do, we need to define some things. First, we need to define there are two issues: extra work during the week and extra work at the weekend. So let's make up some variables. Let's say X here would represent extra hours during the week, and let Y represent extra hours during the weekend. Once we've done that, then we can look at the situation and decide what's going on. He must work some extra hours. We don't know how many he's going to work, but he has to work some extra hours. So we can start out by saying extra hours in the week has to be more than or equal to 0. Extra hours on the weekend must also be more than or equal to 0. Those things are true. However, we notice that his wife does not want him to work more than 4 hours on the weekend, and he doesn't want to work more than 7 extra hours during the week. So X here, extra hours during the week, has to be less than or equal to 7. And Y, I notice that this should be a Y. Let me fix that quickly. Y should also be less than or equal to 4, because his wife doesn't want him to work more than 4 hours on the weekend. So we have those four inequalities. And the final one, he cannot fit in more than 10 hours of extra work. So when you add the X hours and the Y hours, you cannot get more than 10 hours because he can only fit in 10 hours of work during the week. These are our constraints. These are the conditions within which he has to work. These are the boundaries that he has. These are the considerations that he has to make, etc. So these are his constraints. There's one more thing called the objective function, and that function concerns his salary. So or his wage. If he works in the week, extra hours in the week, he's paid $4. So we can have 4x, and extra salary on the week, wage on the weekend would be 5. So this little thing here, we call it our objective function. We're going to talk about it a little bit more. The objective function is what you will use at the end after you would have drawn your graphs and selected your points, etc. The objective function is what you would use to optimize, to decide which combination of hours you should work in the week and combination of hours to work on the weekend in order to make the best salary so that he can pay off his debts, to keep himself happy, and to keep his wife happy. So this is a very important function. But we do not graph this one. These are the ones that we would graph. We graph the constraints. Let me write that down. Graph the constraints. Of course, we're not going to draw the graph now. We're going to look at those in a separate video. Now let's look at another question and see how we can get some constraints out of it so we can understand a little bit more what we're talking about. Here, a gardener wants to plant no more than 10 rows of tomato in his garden, but he wants to plant at least 1 row of tomatoes. His son would like to plant at least 2 rows of corn. Unfortunately, the garden can only accommodate 14 rows of plants. When they sell the vegetables, they will get $30 for each row of tomatoes and $20 for each row of corn. How many rows of each crop should they plant to receive their maximum return for their produce? And so this is a typical question, again, for this kind of topic. When CXC gives them, though, they do not tend to give them like this. They tend to break them in parts A, B, C, D, and make it simpler for the student to do. And so it's a lot more manageable that way. So let's decide here what we want to represent what. We're talking about rows of corn and rows of tomatoes. So let X here be rows of tomatoes, and let Y be rows of corn. All right, so let's look at the situation. A gardener can plant no more than 10 rows of tomatoes. So tomatoes cannot pass 10 rows. So let's write that. It cannot pass 10. So X is less than or equal to 10. Cannot pass 10. But he wants to plant at least 1 row. So he cannot plant more than 10, but he wants to plant at least 1. These are tomatoes. All right. His son would like to plant at least 2 rows of corn. So corn, that would be Y. Y would have to be greater than or equal to 2 because his son wants to plant at least 2 rows of corn. Unfortunately, the garden can only hold 14 rows of plants. So when we add the number of rows of tomatoes and the number of rows of corn, that number cannot pass 14. So let's see if we have everything. No more than 10 rows of tomatoes. Here it is. At least 1 row of tomatoes. Here it is. His son would like to plant at least 2 rows of corn. Here it is. And the garden can only accommodate 14 rows. So these together now form our constraints. Let me write that a bit better. These are our constraints. All of them together make up our constraints. So these are the limitations and the boundaries in which they have to work. Now, an objective function is given there in the terms of how much money they will make from what. So let's call it profit. And you could call it wage or whatever. The profit here is that for each row where they sell the vegetables, $30 for each row of tomatoes, so we can have 30x, and $20 for each row of corn, so we can have 20y. So now we would use this function to decide what combination of rows of tomatoes and corn should be planted in order to make the maximum profit. So these are the ones that we would graph. Of course, I said we're not going to graph them. That comes up in another video. But this is how we look at a question and write down what the constraints are. Again, when you look at the CXC questions, you will see that CXC breaks them down into pieces to make it easier for the student. But this is generally how a typical question is written. Now we're going to talk about the feasible region. Once you have correctly drawn your graph, and I am emphasizing correctly, Then we find an area of our graph. Some persons tend to shade in a different way. And let me explain what I mean. If, for example, we want to say x is greater than 1, then some persons, in setting up their graph, this is the y-axis, this is our x-axis, and let me put 1 here. There are some persons who would say, this line is x equal 1. Shade the part that you don't want. So x is greater than 1 would be over here. So they would say shade on this side, on the side that you don't want, which would be on this side. And then there are other persons of the totally different opinion to say shade the side that you do want. I am in the camp that says shade the side that you want. So since we want x is greater than 1, I would actually shade this side of the graph to indicate where we are talking about. So x is greater than 1 means all the numbers on this side. And if you wanted to put in another line, say for example, x is less than or equal to 5, then I would put 5 here for argument's sake. Of course, you'll be doing this on graph paper. And to save you time, CXC normally just gives you the paper, so that you don't have to waste time. X is less than 5. We want this area, and so we shade in this area. And so typically, when you draw your graph, you'll be shading an area. Now, this one is already done. So the parts that were shaded all intersect in this space. Here we see these two coming together to intersect right here. These here have all intersected in this section. And this section is what we call a feasible region. The feasible region contains all the possible solutions to the problem at hand. So whatever the situation is that you were discussing, for example, in the previous example, we were talking about corns and tomatoes. This particular example would if this were it, all of these points in this region, every single one of them along the lines and within the region would represent solutions. So this is what we call a feasible region. It's the region that has all the possible solutions. However, in practice, we do not consider all the possible solutions to be viable. What we look at are solutions on the outside. That is, we look at the vertices of the region. And so this region being triangular would have 3 vertices. And so in order to decide whether we want to optimize, to minimize, to maximize, we would look at the values on the outside. So in practice, only the extreme values or the values on the vertices are considered. So whenever we draw our graphs and we shade, we're going to look at that a lot on the examples in the next video. These are the extreme values that we consider, and we would then plug these 3 pairs of values in our objective function and decide whether we want to give the maximum wage or the minimum cost or etc. So this is what we call the feasible region. It is that area where all your solutions lie. But in order to find the answers that matter most, we look at the extreme values on the vertices. Now for this last bit, we're going to talk a little bit about how to maximize with an objective function or to minimize. Now here, we have 2 situations. And we are told to find the pair of coordinates which give the maximum value and state the minimum value. And that's what we're going to do. Here we have what we call the objective function. It's given us 2x plus y. And here we're given us 3x plus 2y. And that is what we'll use to decide what is maximum and what is minimum. So look at this region. In this example, the outside is shaded. And so here in the inside is where your feasible region is. So this is our feasible region. And within that feasible region lies all the solutions. But for this example, in practice, like we said, we're just going to pick the extreme values. So we're going to look at the coordinates. Now, what are the coordinates on the extreme values on this region? There's one here. Let me just mark them. One here, one here, one here, and one here. Those are the extreme values. So this first one here is 0, 0. The second one here is 0, 2. This one here would be 5, 0. And this one up here is already written down for us. It's 4, 7. So if we are going to maximize and minimize, then what we do is that we take these values and we plug them into the objective function. And remember that each coordinate pair has an xy number. So xy, 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 just writing them in for now. Each coordinate pair has an x and y number, and our objective function is written both in terms of x and y. So let's see how we could maximize or minimize this. If we want to maximize or minimize, we substitute these values into this. So we have 2x plus y, and we're going to substitute the values. Now, in the first case, we have 2 times 0 plus 0, which gives us 0. In the second instance, we have 2 times 0 plus 2, which gives us 2. In the third instance here, we have 2 times 5 plus 0, which gives us 10. And in the final instance up here, we have 2 times 4 plus 5, plus 7. And that gives us 8 plus 7, which is 15. Now, if we want to talk about maximize, then maximize means the most. So which pair of values here would maximize? This pair of values would maximize. So state the pair of coordinates which will give you the maximum. The pair would be 4 to 7. 4, 7 gives maximum. And in terms of minimum, the coordinate pair 0, 0 gives the minimum. And that we can see based on the answers we get. 15 is the maximum number we got, and 0 is the minimum number we got. Let's practice that a little bit again with this one. Here our objective function is 3x plus 2y. And we're going to look at our extreme values. This is our feasible region, this triangular region. So we have 3 extreme points. The first one here is 0, 2. The second one here is 4, 0. And the third one written up here for us is 10, 6. So we're going to plug these values into this objective function and see which one gives us the maximum and which one gives us the minimum. So our x and our y. So for the first one, we have, for this one, we have 3 times 0 plus 2 times 2. That gives us 0 plus 4, that's 4. Here, for the second one, we have 3 times 4 plus 2 times 0, that gives us 12. And here, for the third one, we have 3 times 10 plus 2 times 6, that will give us 3 times 30 plus 12, and that would give us 42. And so which pair of values gives us the maximum? It is this one. So the coordinate pair 10, 6 gives us the maximum. And the coordinate pair 0, 2 gives us the minimum. And so, like I said, for this topic, linear programming, what we're called upon to do is to read a situation, write down what we call constraints from the situations that are described. Once we write down our constraints, we move to the step of drawing our graphs and shading and finding this feasible region. Once you find that feasible region, now we use the extreme points along with our objective function to decide what is the situation that will give the person in the question the best possible outcome, if they want to maximize or if they want to minimize. Look out for the next video, because in that video, we're going to be talking about the CXC questions and going through actual examples with the graphs, writing constraints, graphing them, and showing how to use the objective function to find the best possible outcome. Thank you for watching and continue to work hard.